A cone rolls uphill. A chain climbs out of a jar before it falls. And a curved slide beats a straight slide in a race. None of these scenes break physics. They break the shortcut your eyes are using. In each case, the visible motion points one way, while the rule that actually controls the motion points somewhere else. That is why these demonstrations work so well on video. You do not need a long equation to feel the contradiction. You see the object move, your brain predicts one outcome, and then the object does something that seems to violate the prediction. The goal of this video is to slow down that moment and show the hidden variable in each scene. That is the trick behind many great science demonstrations. Your brain locks onto the surface of the object, the shortest distance, or the part that is moving most dramatically. But physics often cares about a different quantity: center of mass, momentum, energy, or time. So the cleanest way to understand these demos is not to ask, which way does it look like it is going? The better question is, what quantity is actually being minimized, conserved, or pushed? That question changes the whole story. A surface can rise while the important point drops. A falling section can hide the force that launches a new section upward. A shorter path can lose to a longer path if the longer path creates speed earlier. So we're going to treat each demonstration like a visual mystery. First the impossible-looking event, then the variable your eyes missed. Start with the double cone. On camera, it looks like the object is climbing the ramp. The rails rise in the direction of travel, so your eyes call that uphill. But the rails also spread apart. As the cone moves onto wider rails, the contact points slide toward the narrow tips of the cone. That lets the middle of the cone sink lower between the rails. The outside edges rise, but the center of mass drops. Gravity is not confused. It is pulling the object toward lower gravitational potential energy, exactly as usual. A useful control is a cylinder on the same track. The cylinder has the same radius along its length, so the widening rails do not lower its center in the same way. It behaves more like your intuition expects. The double cone is different because its radius changes from the middle to the tips. That geometry makes the word uphill slippery. The rails can be physically higher at one end, while the center of mass is lower there. The only unusual part is the track geometry. If the rail angle, ramp angle, and cone angle are not tuned correctly, the demo fails. So the honest sentence is not, "This cone rolls uphill against gravity." The honest sentence is, the cone rolls toward the direction that lowers its center, even though the rails make that direction look uphill. Now look at the chain fountain, often called the mold effect. A bead chain starts inside a raised cup. You pull one end over the rim, let it fall, and then the falling side keeps dragging the rest out. The strange part is the arch. The chain does not simply slide over the rim. It leaps upward first, like a tiny fountain. A tempting explanation is to say the falling chain is just pulling the rest behind it. But the research story is more subtle. Biggins and Warner argued that the chain also needs an upward reaction from the pile or support. Later work showed that the exact kick depends on the chain, the arrangement, and the local twists. So the safe version is this: the fountain is not suction, and it is not magic. It is momentum and energy moving through a connected object, with the pile supplying upward motion at the pickup point. That connected object part matters. A chain is easy to imagine as a line of separate beads, but during the fountain it behaves like a system whose pieces are constantly entering motion. Each new section has to be accelerated from rest. If it were only pulled sideways or dragged over a sharp rim, the motion would look very different. The fountain appears when the pickup region gives the emerging chain an upward component. This is also why careful experiments matter. Bead size, stiffness, twists, and how the chain is packed can change what you see. So the video-friendly version is the arch. The physics-friendly version is the transfer of momentum at the exact place where still chain becomes moving chain. The third scene is quieter, but it may be the most important. Put 2 points on a wall. The straight line between them is the shortest path. So if a bead is sliding under gravity, it feels obvious that the straight track should win. But in the ideal brachistochrone problem, the fastest path is a cycloid, a curve that drops steeply at the start, then flattens out near the end. The bead on the curve travels farther, but it gains speed earlier. That early speed pays back the extra distance. The point is not that curves are always faster in real life. Friction, rolling, and track shape matter. The point is that shortest distance and shortest time are different questions. This is why the brachistochrone became such a famous problem. It sounds like a geometry question, but the answer depends on motion. At every tiny piece of the path, the bead trades height for speed. A track that drops sharply near the beginning gives the bead more speed for the rest of the trip. A straight line saves distance, but it does not give that early boost. In the ideal theorem, the winning curve is a cycloid segment, the shape traced by a point on a rolling circle. You do not need the full calculus to see the lesson. Fastest is not the same word as shortest. Put the 3 demos side by side and the same pattern appears. The cone fools you because the visible ramp rises while the center of mass falls. The chain fools you because the dramatic falling side hides the reaction at the pickup point. The curve fools you because the shortest line hides the advantage of early acceleration. In other words, your eyes make a simple guess from the picture. Physics runs the full accounting. That accounting is not less intuitive because it is complicated. It is less intuitive because it keeps track of the thing the picture does not emphasize. Center of mass is not painted on the object. Momentum transfer at the pile is almost invisible. Time along a curve is not the same thing as length drawn on a screen. Good science visuals make those hidden quantities visible without turning the whole frame into a textbook page. That is why impossible-looking science videos are so addictive. They do not show nature breaking its rules. They show us guessing the wrong rule. The best version of the trick is not to stop at surprise. It is to keep the surprise on screen long enough for the hidden variable to become obvious. So which one fooled your eyes the most? The uphill cone, the climbing chain, or the faster curve?